Hello everyone, so nice to be here on the 29th Blockchain Hub. So who is here first time? 1, 2, 3, very good. So I do a quick intro about what the Blockchain Hub Graz is, how it kind of developed, how we came to the point where we are currently standing and what we're doing, and then we have 2 talks today and hopefully a lively discussion. Well, not too many of us, but nevertheless we can still discuss in depth for all what we are going to present. My name is Thomas. I'm here one of the co-founders of the Blockchain Hub in Graz. We did that back in 2016, and in 2016 I was kind of first time looking what is happening in the blockchain space after stumbling over Ethereum, and then I reached out to Shermin. Shermin is heading the Institute of Crypto Economics in Vienna now, and back then she was in Berlin. And together with Jean-Luc in Brussels, we founded the first 3 blockchain hubs in Europe, so in Brussels, in Berlin, and of course in Graz. And from there on, we intended to extend the blockchain hub network. And as I said last time, so we are probably the most active blockchain hub right now. So we have still the resources, we have the things on the internet, and we are doing the regular meetups here in Graz. So basically, whoever is interested in blockchain stuff can come here to the regular monthly meetups. We do basically non-profit. If a non-techie is here, we still try to have the non-techies kind of going into the space and try to show a couple of things here. And of course we talk to a lot of people, so I myself have been to numerous kind of occasions and possibilities to talk about blockchain, which has transformed quite a lot during the last 3 years since I joined. And of course, somebody who is longer in the space knows it changes all the time a lot. A couple of resources for what we have. Basically, the blockchainhub.net offers some information there about basics. So if you have friends who are interested, I usually say, well, go there. The basic stuff is there, and if you need basic stuff, then it's quite helpful to have something to tell them. Otherwise, I usually, if somebody's very technical, I recommend 2 podcasts. One is ZeroKnowledge.fm, and the other one is blockchain. Epicenter Blockchain. So Epicenter Blockchain, those 2 I usually hear myself from a technical perspective. We have also a YouTube channel for Blockchain Hub Graz, so usually all the meetups go there, and here and there something else what we're doing. Then there is a SlideShare channel, so David's slides, and if I have some slides which can be shared, then we put them up there on the SlideShare as well. So in the past, I usually talked about what happened kind of in the space, and that's honestly, it's so much things are happening all the time, just in one space, that it's impossible to cover it anymore. 2016, it was kind of possible to say, well, in Bitcoin something like that happened, and in Ethereum that happened, and Ripple got another kind of problem there with jurisdiction, or maybe whatever, kind of something happened all the time, but you could cover more or less the whole space. Now you have to kind of pick what you want to show, what happened during the last month, and I picked something which I found kind of funny. I don't know if everybody finds it funny, but there was a rap performance with Vitalik Buterin, so who founded Ethereum, and we already know from DEFCON 4 back in November that he can't sing. But it was kind of funny to watch that kind of performance. And why I'm showing this to you, so I hope not everybody has seen it. So probably a couple of them have seen it. But what I like from this community is actually that they don't take themselves so seriously. That's the kind of appealing part. It's not kind of, oh, we are doing all the time just serious stuff. And therefore I find that kind of hilarious to have those performances. So bear with me a couple of minutes hearing them sing some kind of rap performance.
See, we freestyle sometimes. Know your gas limit. Stay within it. What am I gonna do?
So, well, nothing to add. I think it's not going to be a hit, but as I said, so I kind of like this not so taking everything so serious. So it's serious when you want to do cryptocurrencies and make them secure, but nevertheless, if you don't have anything to laugh in between, it's kind of boring. So coming to today's talks, we will hear something from David. He will talk about Honey Badger consensus and will explain us how that works and what's the specialty on Honey Badger. And we also have here Igor from POA Network, and together with POA Network, we the Lab 10 is working on Honey Badger integration into the Parity node software. So that's so he knows also a lot about all the history, all the already done work in the past. And after that, I will talk about the Minerva Burner Wallet, and we can, if you want, play a little lottery game, and we'll talk a little bit more about that afterwards. So let's have David to get started.
So thanks everybody for showing up. I think we chased away a lot of people because of the more technical content of what we have today. What we will talk about is about Honey Badger BFT, which I think is a pretty revolutionary new consensus mechanism, which has got very different properties from those which we are used to. And we will compare those. And for that we will start with a little bit of a historic perspective. And I think no talk about consensus protocols is complete if you don't have the picture of Leslie Lamport on the screen. He's a quite famous computer scientist who is famous for his studies of distributed systems. Amongst others, he described the Byzantine generals problem. He's also very known for his work with scientific publishing tools, above all the LaTeX, which is still used today for most scientific publications, and also his work on formal verification like TLI+. So the most interesting thing for us in that context is the problem of the Byzantine generals. First, a little story about where this name comes from. Actually has nothing to do with the actual historic events, but it still makes for a nice picture. So Leslie Lamport invented it, and he thought about that there was some of his peers had defined some problems which got very famous, like the dining philosopher's problem. And he thought about that the things that he is dealing with are also very important. He wants them to be popular. So he thought, if you want to have the problem you described to be famous within the community, you have to find a good story. You have to tell a good story. So his first idea was to call it, because at that time, in 1982, when he published this paper, Albania was one of the most isolated countries on the planet, and he didn't want to offend anybody with the problem description, so he called it the Albanian generals. And then a friend of his pointed out that there are actually Albanians outside of Albania, which he could offend with it. So he found a different name for it, and that was the Byzantine generals. And it is the setup of this problem is that you have got a city which you want to conquer, and you've got a couple of armies with whom you can only communicate through messages. How can you, and you want to make sure that either all of them attack or all of them retreat. So how do you design the messaging between these armies so that all of them are guaranteed to attack or guaranteed to retreat? And that also has to work in the presence of traitors. So there might be one or more traitors amongst the generals or your lieutenants, which may convey wrong messages, say attack when others say retreat and stuff like that. And there are really two primary rules that have to be true in that environment. All loyal armies have to obey the same order. So all which are not traitors have to either attack or they have to retreat. And if the general is loyal, then all have to follow the order of the general. So these are the two rules which are true for the Byzantine generals problem and also for most consensus algorithms. So here we have got a simple setup, only three nodes, one is the general who gives out the orders, and the others, two lieutenants which have to obey it. And they are attacking Byzantium in that case, Constantinople. So if the lieutenant, so we say we have got three armies and one of them is a traitor. So they are really, we look at it from the view of one loyal lieutenant, Lieutenant 1, and he has to now decide, he gets two different messages. The general tells him to attack, but the Lieutenant 2 tells him to retreat. And he has to decide who is a traitor, who is a traitor. Is it possible? So we see here attack and retreat. In the case when the lieutenant is the traitor, when the general is a traitor, he could decide to tell Lieutenant 1 attack and the other one retreat. So both lieutenants are loyal, but the general is a traitor. And when we go back and forth between the two, you see that Lieutenant 1 cannot get the same messages. He cannot decide which one is the traitor. And in this case, actually with three parties, it's not possible to decide who is the traitor, and he can't fulfill the condition that the loyal lieutenants all have to obey the same order. It's not possible in that case. And if you look at it to prove that formally, Lamport came to this formula, and this is true for most consensus protocols even today, even for Honeybadger, is that the number of the nodes needs to be 3 times the faulty nodes, so the disloyal nodes, plus 1. This is a formula we'll see a lot of time in this talk. And F means if you want to be resilient against one traitor, you have to have at least 3 times 1 plus 1, 4 nodes. Then it works. With 3 it doesn't work. Are there any questions yet? No? Okay, then there was another paper published in 1999, which is called the Practical Byzantine Fault Tolerant algorithm or protocol. Here it was mostly developed in the context of a network file system, for example. So you've got clients which request execution of an operation from the primary node. In this case, we still have a primary node. The primary sends the request to all the other nodes. The node sends responses directly to the client, and the client accepts the result as soon as he gets F plus 1 responses with the identical results. Because in this case, he can say, we only accept F, a number of F traitors or faulty nodes And if you've got one more than that, and they all got the same results, it must be a correct result. If the condition is true, that there are only f faulty nodes. The way the topology can look like in a minimal setup in that case is that you've got one general, and then you've got 3 lieutenants, and they all are directly connected with each other and can exchange messages. So the general gets, a client gives the request to the primary node, which we call in this case general. And the general is then responsible for distributing the information among the network and for the clients for the nodes to come to a conclusion and send the confirmation back to the client. So the PBFT consists of 3 phases. The primary sends a pre-prepare to all the nodes. Then all the nodes receiving a valid pre-prepare send a prepare message to all the other nodes. And after receiving a 2 times F matching prepare messages, each node sends a commit messages to all the other nodes. And after receiving 2 times F plus 1 commits, the node performs the operation and notifies the client. So we've got a diagram how that looks like. So here the general received a request from a client. He sends this pre-prepare message to all the other nodes. And here we assume that one of the nodes is faulty and doesn't send any messages back. And because it's 4 nodes altogether, this still works. So if all receive the pre-prepare message from the general, they send a prepare message to all others, and this way they come to consensus which sequence number, which is sort of like a block number, they will use, that all correct nodes will use the same one. And in the last phase, when they received at least these 2F prepare messages, and you will see it's 2 in all of them, because each node also, of course, records its own prepare message, which means when he gets only 1, in this case from lieutenant 2, then he still has 2. He's got his own one and the one from lieutenant 2. So the condition is fulfilled. And in the next stage, he gets 2F plus 1, which means he records his own prepare commit message and gets 2, in this case from the general, and lieutenant 2, and has got 3, and he can commit the operation. So this is how the PBFT works. Are there any questions for this at this point? No? Yeah?
Would the general also send out messages during the pre-prepare phase?
No, I mean he only gets the general receives all the requests from the clients.
Yeah, the pre-prepare phase.
Mm-hmm. So he sends out he's the only one who sends also out pre-prepare messages. Okay. And to all the others. And since he himself doesn't receive a pre-prepare message, so he can't send a prepare message. And that's why in this case it's only 2F. But in this case, in the last stage, in commit phase, the general is included again, and then it's 2F plus 1. Mm-hmm. So that's PBFT. And here we have got the same formula again, 3 times F plus 1. And the explanation in the paper was quite intuitive. If we say that F clients or F nodes can be faulty, then that it must be possible to proceed when you get n minus F replies, right? But if we proceed when we get n and n minus F replies, we can't assume that all these n minus F replies really came from correct nodes, from loyal nodes. They could actually come from the faulty nodes, which means we can only assume that n minus F correct replies are there. And even in that case, we must be sure that the replies of the correct nodes are really outnumbering the ones from the incorrect nodes. Which leads us to the formula that n minus T2 times F has to be greater than F. And that the smallest number, natural number, greater than 3 times F is 3 times F plus 1, which leads us to this formula. So this is an intuitive way to understand what it is. In the paper, of course, they warn against these intuitive explanations, which can quite often be misleading, but the formal proofs also lead to the same number. Are there any questions about that? No? But PBFT also has got a couple of drawbacks. One is that there's a single proposer and leader per round. And this proposer could be a faulty node. It could be a Byzantine node, which sends out wrong messages or sends us transactions or submits empty blocks or no block at all. So he could, if there are no other mechanisms, a faulty node could block the chain from proceeding, and that's why it has to have some conditions where it says if there's no block produced for like 5 minutes, it has to switch the leader. So this leader has to be switched over. Of course, when it has to react, when a network has fluctuations in performance, these limits, these time parameters might keep the whole protocol from proceeding completely, which means it has to, in many cases, dynamically adjust the block times to even work in adversarial, in harsher environments. Let's look at the honey badger. How does it solve the problem? The honey badger BFT algorithm was published in 2016, and the revolutionary thing about it is that it doesn't need a leader. So it's everybody is a leader in this protocol. It's also resilient against censorship. It's also asynchronous. Which means it doesn't have any time parameters. It doesn't say that there has to be a block every 5 seconds or every minute or something like that. It just goes as fast as the network allows. And how does it do that? So it looks like this. It's completely symmetrical. So in the case of PBFT, you would have a general and 3 lieutenants. But in the case of honey badger, all the nodes are equal. So all the nodes will receive transactions, all the nodes can talk with each other, and all the nodes collectively create a new transaction block, or a new block, and come to a decision together at the same time. So every node proposes a fraction of the transactions in this case. In PBFT, for example, every node it could be, for example, like in Hyperledger, that it's just an authority round, that every node, when you've got 10 validators, that every one of the validators will make 1 block. So it's just round robin the whole time. But in honey badger, every node proposes transactions in every round. And for practical reasons, for example, if you've got 10 nodes, then each node contributes 1/10 of the maximum size of a block. So if a block would be 100 transactions, then every one of the 10 nodes would propose 10. So it makes sense. Then to make sure that that the transactions cannot be censored, the transaction proposal is encrypted using threshold cryptography, which means before every node sends out his contribution, he encrypts it so nobody else can see it. Then, because of how many of you know about threshold encryption, how it works roughly? Yeah. Okay, then we will go more in detail into that later. But for now, we just say that nobody can see these encrypted transactions until the block is actually finalized, accepted.
Little question.
Yeah.
Now, is it possible that different nodes propose the same transactions because I don't know that the transaction you propose is the same as I do?
Exactly, yeah, exactly. I will go into it in the next slide as well. Of course, in this case, no single node can stall the progress. So you always make a progress. I mean, you may not have all the transactions of all nodes included, but you still make progress always. And one property which is interesting for block rewards, for example, is there's no single block author. In many other consensus algorithms, like in PBFT, you always have a block author and you give him the block reward. But in this case, there's no single block author. All the nodes together, they author the new block. So this is a visualization how you can imagine how this works. So we have got 4 nodes in this case, all give a contribution. In this case, it would be like 25% of the transactions which should be in the block. They encrypt these, go through the consensus algorithm, and at the end of the consensus algorithm, they've got all the secret shares to decrypt it. And then they, of course, have to look at what everybody submitted, because only at this point you know what has been proposed by everybody. And they could, of course, all of them send the same transactions. Yeah? So you have to do a deduplication at that point. And of course you have to verify. Because if one of these is a traitor, of course he can, in his contribution, he can write whatever he wants. It could be complete garbage as well. But it can't destroy the whole block. So if one sends invalid transactions, for example, then the other 3 would still be included and it would create a block. It wouldn't be a problem from that point of view. And of course, the decryption, the deduplication, and the verification has to be same in all nodes, so that the block or the transactions that come out have to be in the same has to be the same transactions, and they also have to be in the same sequence, so that they all can create the same block at the same time, because otherwise it wouldn't work. Is some questions about that part? Yeah.
What about conflict? So let's say there's a transaction that node 1 and node 2 get, but this transaction has different outcomes. Or like I produce two transactions that are conflicting with each other. And node 1 puts it in their contribution and node 2 puts it in their contribution. How does the network then decide which one was node 1 the illegal one, or was the one that node 2 submitted the illegal one? Yeah, I mean that has to be done in the verification step here. Yeah. So if 2 transactions conflict, which one gets kicked out?
I mean the order. I mean in principle, if the honey badger algorithm produces a sequence of transactions, then you hand that to the in this case to parity, and parity will decide which one is actually valid and which one is not. So in this case, it's actually the same as in every other consensus algorithm, and the system, or the underlying system, has to decide what is valid and what is not valid.
First come, first served.
In this case, probably.
But there is no first. It's in the same block.
But it has to work to it in some kind of order. Else, or you have to click both.
Yeah, I mean.
Yeah, you could kick both out.
Or you take one first and the other one is not working because.
Yeah, but then it depends on, like it has to be the first in every implementation, right?
Yeah, it has to have exactly the same order. Yeah, absolutely. Yeah.
Then I can know if I send out 2 conflicting transactions, which of those will be the first.
Yeah. And that has to be decided by the underlying implementation, because Honey Badger BFT doesn't deal with the Ethereum virtual machine and stuff like that. It's not in his in a part of his specification.
Okay, so this will just be kicked out at the verification stage.
Yeah. So the verification will have to be run by the underlying system, not by Honey Badger.
And also there is verification before the node gets the message. So before the node will get the message and try to add it to, let's say, to the block to verify it.
So you mean from one node it would not be possible to have basically 2 conflicting transactions within?
In Ethereum you have nonces for this, right? If you have you open the transaction with larger nonce, and on your node, before you start to send this transaction into contribution, just take the highest nonce, right? And nonce is already signed by the originator of this transaction.
Yeah, but I would be the originator, and I send a transaction with the same nonce to one node in Japan, and at the same time to one node in London. There is no time for them to verify that this transaction actually happened on the other side of the world. They both get it at the same time, and they both propose it. It just has different outcomes. Once I pay Thomas, and once I pay David.
Oh, it's different transaction.
Yeah, it's a different transaction, but it spends the same amount, so that was spent.
Well, yeah, there is no such thing in Ethereum. It's like it's account-based system. It's not UTXO-based system. Well, but yeah, Honey Badger technically.
I have 10 ether. I spend 10 ether to him and 10 ether to him with the same amount.
It's two different transactions. Whichever will come first will be accepted.
Yeah, they both come at the same time because both node 1 in Japan and node 2 in London propose this transaction. Because it's the only one that they know from me.
Yeah.
Processed in the same block, but it's not processed at the same time.
If they process in the same block, then you will pay both.
They don't have the balance for both.
I don't have the money for both. I have only money for one of them. So which one gets processed first?
Then it will be. Well, it depends on the validator, right? Which one can put.
Yeah.
Someone
Yeah,
has to select which one is first.
Yeah, I mean, Honey Badger, the only thing that Honey Badger makes sure is that the sequence is absolutely the same for all of them. Yeah. Verification is then the system of that's the client has to do.
So they will come to the consensus that these two are proposed,
Yeah.
and whatever then the implementation of the verifier says, gets in.
Yeah.
Most likely they will agree on set of transactions before they start to.
But how? Like Honey Badger is the way to agree on which transactions.
Yeah, I mean,
they agree on the set first, and after they you can look at the system with like all nodes, right, and on each node, right. Like when you look at one node, you don't know what other people agreed, right. And that's why you need Honey Badger to be sure that everyone agreed on what you agreed on. So if you have some, queue between all nodes and transactions, and you think that all other nodes have the same set of transactions, it doesn't mean that it's true, right? Because we can have faulty nodes, as you described before. The only way you can be sure after the consensus made this work to reconcile this data, right?
Yeah, but even in the presence of faulty nodes, the sequence of transactions that that the outputs will be the same. Okay, then we've got from the Poor network. It's got a great animation about how threshold cryptography works. In this case, we have got like 4 parties which all participate in this threshold encryption. So we've got Alice, Bob, Carol, and Dave. If Alice creates an encrypted message, and it was configured that two parties are enough to decrypt the message, then Alice could encrypt it and send it to Bob, Carol, and Dave. And either two of them can then decrypt the message. So it could be Bob and Carol, or it could be Bob and Dave, or Dave and Carol. They would be enough if they have got their secret share, their shares, their encryption shares. They can use threshold encryption to get the message from Alice. But they can only do it when they cooperate. And that's a mechanism that Honey Badger is using to make sure that all the clients only are able to decrypt all the transactions when the threshold for the consensus has been reached, which means when the block has been accepted. Which means the content of the transaction is only revealed when the block is already finished. Which means nobody can previously know what's in it and censor it beforehand.
If there's some network issues, and I'm not in contact with as many nodes as I would expect, and I'm not able to reach the threshold, what's happening?
Now, that's the same with all I mean, that's a condition we set up front, you know. We say there are only F faulty nodes. If there are more than F faulty nodes, then we got a problem.
Or does it lower the threshold after some time?
I mean, that's a fundamental property of the consensus algorithm. So if you have got more faulty nodes than it accounts for, then yeah, things go wrong.
Whatever is faulty, it might be that it's just not reachable yet.
Yeah.
So it just delays the finalization of the block.
So the block is created if I get enough participants back.
Yeah.
So if I have 20 nodes in North America and 20 nodes in Europe, and the fiberglass scale is broken in the middle, and they're not able to reach the 30 nodes they need, then someone have to repair it or satellite before this is happening. No block is created.
Yes.
Exactly. Yeah. And that's really the advantage of the honey badger. Yeah. Because as soon as the connection is established again, it can continue.
Most likely the network will slow down and shut down. Because TCP/IP is giving us so many possibilities to route messages between nodes in open internet. So most likely, if someone doesn't like your network will be slow, but not.
Yeah, but that's a good example because it shows the advantages of the honey badger. Yeah. Because the honey badger consensus, it just continues at that point, while other synchronous consensus algorithms will try to adjust the time for the blocks.
To create a block, and so you will have Europe and the USA chain.
Or
once they find together again, then they have to make a relock.
Or they can't make, or they stall. They can't make a block.
Consensus with leader, you need to DDoS only one node of leader, right?
Yeah.
To fall back this consensus to another protocol, how to relay the leader.
Yeah. Or they do something. They make the block time longer and longer and longer. You know, it's like 5 minutes, 10 minutes, 20 minutes, and so on. Yeah. And then the network runs at full speed again. But it's still at this 20 minutes, and then it has to go slowly down to the original performance. While Honey Badger goes as fast as it goes on the spot. You know, as soon as the network runs again, it can progress again, and that's a great thing about, great property about the Honey Badger.
Sorry, does this mean Honey Badger is not creating a block if there is no one have a demand to send a transaction?
That's a different thing. That's completely how you trigger a new block. That you can configure it. You can configure it by maybe time. Yeah, you can make an empty block if you want to.
There can be some kind of heartbeat.
Yeah, you can.
No one requests.
I mean, it's up to you. If you're in charge of the implementation, you can do anything you want. One of the triggers would, of course, be a certain number of transactions is available, and then start making a block. Or it could be time triggered and said we want at least every 5 minutes we want to have a block. We can do that as well. Because of course these contributions could be empty. You don't even know what's in it. So it could be empty as well.
It can be used not only in crypto, right? It can be, you can think about like 4 IoT devices, right?
Yeah, and that's one of the great properties of the Honey Badger as well. I mean, there are networks which are extremely where the conditions are just really bad for consensus algorithm protocols, and that's for example the Tor network. Yeah, where the performance of the network is fluctuating wildly. Yeah, and where many consensus protocols would have big problems, Honey Badger can still make progress. Just continues as fast as the network allows it. So
my contribution to a block cannot come too late. So if the block is created before my contribution is arriving, then it's a contribution for the next one.
It's in a queue.
Well, and you have to make a new. You have to. I mean, it's every block is an epoch, so you'll probably have to. I mean, if your transactions are in the transaction queue, then it will just be put in the next. Yeah. So, now a little bit more detail. How does this work in the flow? Every node is equal. So every node has got or every verifier, every node that participates in the consensus protocol has got a local transaction queue and accepts transactions from clients. Then when a new epoch starts, it selects transactions for contribution. And usually, to prevent the problem that we mentioned here, that everybody sends the same transactions. So we've got like 10 nodes which all send the same transactions, so you have got really limits the number of transactions that you will have in the block. The transactions are chosen randomly in many cases. So if you got like 100 transactions in your local transaction queue, and the block size is 100, you randomly choose 10 of the top 100. So you minimize the overlap with the other nodes. So once you have got the transactions selected, you encrypt them with threshold encryption, and then you start broadcasting those to all the other nodes. And of course, you receive broadcasts from all other nodes. So you collect shares from all the other nodes as well. As a next step, when you have got those, then you have to come to an agreement which ones of these shares, of these 10 other nodes, will be included. And that's a second step called binary agreement. And once the binary agreement step is finished, all of the correct nodes have concluded on on which of the 10 contributions will be in the block. So and at that point you also have got enough shares to do the decryption. So at this point you have decided what transaction shares will be in the block. You have got enough shares, secret shares, to decrypt the contributions. So you will end up with the final list of transactions which will be in block, which everybody has got agreed upon. You go into this deduplicate and verify step, and you come up with a list which will be the same for all nodes at the same time. And this one you then have to seal, of course, as well. There's another step where you seal the block, also with threshold cryptography. But this is basically the flow that happens in the Honey Badger consensus protocol.
Why would I, as a participant, not select all transactions? Because it takes too long to transmit it compared to someone who selects only few.
Well, I mean, if you set the rule that of this. The rule you set that only like a fraction, if you have 10 nodes, then you only can contribute the tenths, then you misbehave. You would misbehave if you send 100 if you're only allowed to send 10.
But they don't know it until they decrypt it.
Yeah. And you could send nothing as well. You could be a faulty node. I mean, you could not send anything. It's all up to you. But you would basically be a Byzantine node.
Okay, yeah, but if I really submit all valid transactions that I know of at the moment,
yeah,
then that would be fine behavior, because they either get duplicated or they are valid.
Well, I mean, it's not allowed, yeah.
Yeah.
It's not allowed.
You miss. You're still misbehaving because you submit too many transactions.
It's a scarce resource, network traffic between validators. So you overutilize scarce resource.
But how do you know what is the correct number?
Yeah, I mean, these rules are set up front, of course. Yeah.
No, I mean, the queue is so transparent
I
that
saw 1,000. I sent the 100, the 10% of those.
Yeah, but you know how many nodes there are. I mean, you're one of the validators.
Yeah, I'm one of 10 nodes.
Yeah.
And I see 1,000 transactions, so I sent 100. All the others send 10 transactions because they only know 100 of those 1,000 transactions.
But then already something with your node is wrong. Why you see so much different amount of transactions?
It doesn't matter.
I'm behaving completely logical from what I know of the world.
No, because it doesn't matter how many transactions you have got in your queue. What matters is the block size is defined. How many transactions can be in block is defined, and how many validators there are is defined. It means that it's uniquely defined how many you can put in.
So basically, the gas limit defines how much you are allowed to put in, or to send it actually. In our case, right?
Yeah, I mean, you've got a contingent for the block, and you know that you can only contribute 1/10 of it if there are 10 nodes.
Okay.
So the maximum size divided by the amount of validators.
Yeah.
And then I'm only allowed to contribute my share.
Exactly. Yeah. And otherwise you misbehave.
Then it's very unlikely that this maximum size will ever be reached, right?
Yeah, it's an unlikely. Yeah, I mean, I think they describe it in the paper as well, and they say that it's very unlikely that it's less than 1/4.
You have to do some overbooking.
Shouldn't there be some overcommit? Like I said, 15% of the total amount instead of 10%. So there is some chance that the maximum amount will be reached, because the verify step, I would say, would anyways cap it.
Mm-hmm. Yeah. But I mean, according to the paper, that's the rules that are set in the paper. If you're the implementer, of course, you can change any parameters if you want to.
So you could also say the block can be gas limit like 10 million.
Yeah.
And you anyway expect only 8 million. Or
Yeah. I mean, the only thing that you have to assure the only thing you have to assure that after all these. The blocks, the transactions and the order of the transactions is exactly the same for all nodes. That's the only thing you have to make sure that's there. Okay, are there any more questions about that? Bill? Yeah?
So how do you scale this kind of protocol? I mean, if you have thousands of nodes, it's a hard time. I think it's hard to really broadcast it to all of the nodes.
Yeah. I mean, these two steps are expensive. Yeah.
So
sure. You can't. You can't.
For cryptocurrencies, there are some studies like how many validators do we need in a public decentralized network, and there's a study by Cornell called Decentralization of Bitcoin and Ethereum, and they figure out that 20 or more nodes in the public system with from a quorum consensus is more decentralized than current state of Ethereum. So if we think about cryptocurrency, we should think about orders of tens, right? And if you look into other examples, like EOS, 21 validator, decentralized, protect billions of dollars, and some other networks. It's all around like 10 to 50 to 100. I didn't see examples of thousands of validators.
But I need some way of selecting the subset of.
Yeah, there are some ways like the VDF verifiable delay functions used to produce randomness in chains like Ethereum 2.0, where subset of validators can be selected for each epoch, and each epoch can be, I don't know, let's say 100 blocks or 1 week, right? And for this week, we have some number of validators, I don't know, 20, right? But we have a larger group of validators, which are like waiting for the time to be selected into the subset. So so what it gives to us, it gives us inclusive participation in a set of validators, right? Because it's a big problem for many chains with limited spots where we have exclusive groups like 21 validators in EOS. Get lucky to get in, right? It's quite hard. But if we have this large set of validators, thousands of validators, and randomness which selects subset, and also there should be some reporting of faults, because if someone selected out of nothing, it's more likely that this someone will cause some consensus faults, right? Yeah, that's it's not possible in modern consensuses to have thousands of nodes working because of limitations of message broadcasting, right?
Yeah.
Well, I don't know if you get into this one for Honey Badger, but the other kind of thing of scaling means usually this kind of transactions per second. And if you look at that kind of number, Honey Badger is extremely good, because you can create fairly big blocks, and they demonstrated quite massive kind of transaction throughput through that protocol. So.
Well, Yeah, I'd say that almost any protocol will brag about about the high transaction per second before first punch in the face, right? And after censorship-resistant consensus like Honeypage can actually deliver, right? That's why we were interested in exploring this consensus and put work in implementing it.
Yeah, even delegated proof of stake, what you have in EOS, I know from people that the kind of bragging numbers are not necessarily reached in live environments.
I mean, there are two kinds where you can scale. Like one way would be, okay, it's easy to have many participants in the consensus itself. So you have more people that vote. You have, let's say, instead of 20, you have 200 or 5,000 or whatever, which is quite hard. Or you rather have a larger amount of data that you can come into consensus of. So instead of just deciding one bit and saying, oh, okay, it's 1 or 0, you can decide upon 1 whole megabyte per round or whatever. So that's where these transactions per second come into place. So if you can decide upon a bigger amount of data at the same time, then you get more transactions per second, so the users of the system can put in more into the system. And even if there's some little defects in there, the system might still work fine, because the verify phase is easy to do or whatever.
Mm-hmm. Yeah, and
it's not easy to have dozens or let's say more than dozens of participants in any BFD, in any Byzantine fault tolerant system that I know of. So usually you would be more into the, do we now deploy 7 or 8 nodes or so? I'm not like, okay, let's spin up our Amazon account and let's throw 5,000 instances on this problem.
Yeah, and the other thing, as we mentioned, if you got a reliable randomness on the blockchain, then you can, in each epoch, select a sub group of it and then still have 1,000 validators, but they are not all working at the same time.
And you're not CBIL resistant, so someone could spin up 1,000 of them and have a very high chance of being in the random set.
Yeah,
usually you have some staking there.
Yeah, so usually you would also need to put in some deposits, so putting up 1,000 instances is prohibitively expensive.
Mm.
How many nodes can run at the same time?
Oh, we come to the performance in the next slides.
Okay.
Mm-hmm.
Yeah, and if there's no block times, does that mean if there's still transaction waiting to come into a block, blocks are chain firing? And
you can.
If they're chain firing, what is like the technical minimum time between?
I mean, the technical minimum time is how fast the network can go. So if you've got a very fast network, you can go faster. If it's a slow network, you can go slower.
They all have to agree that we finish now a block before they start with the next one. So this
yeah.
Basically the delay until everyone agreed.
Yeah, I mean, there's a possibility. There's a possibility that, I mean, at this point you've got a finalized list of the transactions, but you still have to seal it. And there's one possibility, one optimization is that you, before even the next, this one is sealed, you start the next one. That's possible.
While I'm working on sealing or creating a block altogether, I'm still receiving new transactions and buffer them. And once I fire this transaction, we start to build the next block. Yeah,
I mean, as I said, you can be finished, yeah, and then you have to seal it, and seal will also need some network traffic. But at the same time, you can start with the next one.
But it doesn't start while we're sealing the former block, because we know there's no other transaction coming in. It's just the final phase. Do we already start to creating the new one simultaneous?
Yeah.
So we are faster.
Yeah. Okay. So you already enter this this pipeline when this is finished, even if it's not sealed.
Okay.
Mm-hmm. So that's an optimization that you can do.
Does this mean that if there are 3F+1 faster nodes that I will never be able to participate?
Yeah, of course. I mean, it can.
You would be faulty.
Yeah.
Faulty.
You would be faulty because you're
coming
too slow to
too late.
Yeah.
Always too late.
Yeah.
It would be your fault.
Yeah.
It doesn't mean that this is the wrong thing. It's just
yeah, I mean that's something we just discussed as well. I mean, who gets the block reward in that case? Yeah. I mean, if you are, for example, somewhere in Mongolia or something, and you never participate because you're too slow to participate, will you still get a block reward? That's an open question. I mean, yeah, I mean, in this case, it probably would get something. Yeah? If you don't add an extra penalty for that somehow, yeah, everybody would get a block reward.
In round-robin algorithms, it's very common when people deploy their validators not on slow hardware, and they didn't fit in like 5-second blocks, then they don't get a reward, even they
oh yeah, that's for sure. But what do you do in Honeybadger? If somebody is so slow that he never gets to participate in a block, for example, then how do you deal with that? Can you?
Yeah. But you know who is a contributor. So you can just say who didn't contribute is not earning.
Yeah, but then for every block, F nodes would not contribute.
Yeah, I mean, it's of course the one with the slowest node will never get anything. It's meant to be.
Yeah, but if you assume there are like 3 F+1 nodes in the United States, then I won't be able to participate from Europe because my internet connection will
exactly. Yeah, that's what we discussed. That's what is discussed today as well. It actually creates an incentive to concentrate all the nodes so they're close to each other and have a lower latency. It rewards those who put their nodes in the same.
Or you can slow down the network to give them a grace period to contribute.
Well,
I don't know. Yeah.
In Bitcoin, most created blocks sent through the exclusive network, which are available only to Bitcoin miners. And they created their own low latency network, and it's well known. You can submit your block if you're outside of this network and get included into the Bitcoin chain, but most likely other. So it's natural that this tends to centralize. What was the question about?
Yeah, I mean, the question is, I mean, if you have got somebody, if you want to give an incentive that people distribute their nodes across the world, and you have got one node, maybe Mongolia, for example, which has bad internet connection, would you just accept that he gets less block rewards because it's just slower?
People say for privacy reasons they are behind to one network, which makes them slow per definition.
Yeah, so they would get less block rewards.
Yeah, also, I'd like to
or never. No.
Is not defined who are validated, who are creating blocks, right? And also, it's not there is no definition how to reinitialize this set of validators. So we added a sub-protocol to Honeybadger, which we call dynamic Honeybadger, where participation in the set of validators can be determined by some external events, right? In our case, when we integrated into Ethereum, who validators are defined by smart contracts, right? If you're in smart contract and a special set of validators, you're participants of this validator set. And this validator set can be reinitialized, right? And also reporting can go up to this layer up from Honeybadger to smart contracts, and smart contracts can accumulate this faults and initiate reinitialization of validator set, right? Or just remove a validator after the validator set.
Yeah,
so
that's the rewarding right? And usually this removing from the set means that validator who is removed also is losing his stake, right, or ability to participate in reward distribution. So they try to keep their nodes up, not be faulty, and minimize ping between.
Yeah. I mean, and if you are in control of these contracts, you can decide. I mean, if you've got somebody who's got a hard time contributing because he got a slow computer or in a remote, or is running his server in a remote place, you can pretty much decide what you do with him. If you include him or if you want to remove him, it's probably.
The consensus will decide that. Right? The engine will decide, not the.
Yeah, man, but you can write what happens. You can define what happens in that case.
Right, but like these smart contracts, they run on the same node of each validator. There is no central central server for the solidity contracts, right?
Yeah.
So you run on your computer, and you basically agree like transactions which are sending to this contract, and transactions which are deciding on validators that are executed on the same on the same computer as flooding. Right?
Yeah. But I mean, it's totally in your power to say that whenever a block is created, then everybody gets a share, even if it didn't contribute to that one block. That's absolutely in your power to decide.
From the point of view of the algorithm, you would be a slightly or very faulty node. And if you decide to reward it still or not, it's up to whoever designs the reward system.
Exactly.
That's not part of the algorithm itself.
Yeah, reward is not the part of the algorithm.
Yeah, but I mean, what is part of the algorithm is it can record the metrics, and then you can write whichever logic you want on top of that data.
I'm still, or something different connected to that, like binary agreements. How is that done? I mean, how do you reach binary agreement of inclusion?
Yeah, I mean, at this point, after broadcast, all the most of the nodes will have the contribution of the other nodes. Yeah. And then the binary agreement is actually a bit field, which for every node which exists has got either yes or no, either on or off. And the binary agreement is its own sub-protocol, which comes to agreement over all or the majority of the nodes, which ones will be included. So all of them, at the end of the binary agreement, all the nodes which participate and are correct will have the same bit field, and they have therefore know exactly which contributions they will include and which one will be excluded. And that's a nice thing about Honeybadger. It takes things which already existed. While this one loses reliable broadcast, and this was one binary agreement. This is not something that the writers of the paper developed. These were pre-existing protocols, and they just cleverly used them to construct Honeybadger.
There would also be a chance to put in some kind of heartbeat, right? So to artificially slow it down and say, okay, we wait with our binary agreement protocol for every 5 seconds. So slower nodes have a chance to catch up.
You could. I mean, if you are in charge of the implementation, you can set any rules you want.
It's more likely that even slow nodes will still be able to contribute.
Yeah, I mean, you could say that.
And blocks will also become fuller.
Yeah, you could. There's nothing keeping you from that.
No, I think it's not true, because there's this threshold. This means when I get enough input for the threshold, we start to finish the block, or I'm not waiting for more contributions.
Yeah, I mean, you could wait for more, you know. You could wait for more.
Because you know from the thresholds, you reach thresholds of more proposals.
Yeah.
Because you would start as soon as you get from a few. Or even from one, I guess.
Yeah. Okay, are there any more questions to that flow?
Hard discussed.
Yeah, that was an interesting discussion, and many of the problems we already discussed before.
Don't give us numbers.
Give us numbers.
Okay, yeah. So let's look at the performance. And the writers of the paper actually made a pretty good test case. They spun up AWS instances and distributed them over the globe, over the regions, and ran tests with like 32 nodes, 40 nodes, 48, 46, 56, and so on, up to 104 nodes, and recorded the performance if you add more transactions. And you see that with 32 nodes, it's really fast. I mean, here we got 10 seconds, and here we are really in the low. At this point, we are below 1 second. So you can really go as fast as the network allows you to go. But of course, I mean, the more nodes you have, the more communication overhead there is. And when you go up to 104, you are up in the, 1,000 seconds or more. And then it really builds up the time that it takes to make a new block. So at a certain point, it's not feasible to run with Honeybadger either. So, but you see, it's still with 56, it's still quite performant. It's still quite usable. So, and of course, the throughput is nice actually. So actually, quite performant consensus algorithm.
So it can be reached that 56 nodes able to process 10,000 transactions in 15 seconds or something like this.
Yeah.
No, in a minute.
Yeah, that's 100. Yeah, that's 100 seconds.
100 seconds.
100 seconds.
Okay, that's
about 10,000 per second.
less impressive.
Yeah, but still quite good.
How does it compare to Nano or IOTA?
I didn't compare it with Nano and IOTA. There's a comparison with PBFT. And there you see that with 8 nodes, PBFT is faster, but with anything from 16 nodes and more, Honeybadger outperforms PBFT by quite a margin. So in comparison with PBFT, it is more performant, especially with more nodes. With others, IOTA and so on, why not? But it's of course also probably true that IOTA will not have the same properties as Honeybadger has.
Yeah, you don't need trusted instances.
Yeah.
But on the other side, you also can't do smart contracts.
So, are there more questions about the performance or discussion points?
Finality though. So in IOTA you don't have finality. That's a bit of a downside.
Well, this is kind of, I think you didn't mention it, that this is, when you have the block, it's final.
Yeah, I mean, that's a case for both of them, and that's the case for PBFT as well.
Yeah.
Oh, okay. PBFT. Okay. One typo missed. Yeah. Okay. Yeah. And then what are the advantages? We already mentioned a lot of them. There are no timing assumptions, so it just goes as fast as it is. It just keeps going as fast as the network allows it to go. Yeah. Yeah. So even in environments with highly variable data transport performance, like Tor networks, even in Tor networks, it still works. You can still produce blocks. It's a bit slower, but it still keeps going. And there's a censorship resilience, which is a nice property. And you can also implement random beacons with threshold encryption quite well as well with it. So one of the things, there's no proven use in production yet. That's what we are working on. And yeah, are there any more questions?
More a philosophical question. What's the reasoning behind the Honeybadger, the animal being chosen for?
Yeah, well, that's quite clear. Yeah, I mean, even in the most adversarial environments, it still keeps going and going and never stops. Yeah, it's yeah, it's tenacious like the Honeybadger, you know. Okay, any more? Then thank you everybody, and I hope you enjoyed yourself. I think it was a very interesting discussion.
Thank you. Okay, let's go on. I hope I don't scare you away from the beer. So, just a second. So, we will talk about, very briefly, about Minerva Burner Wallet. And so, who does not know the Burner Wallet? 1, 2, 3. Good. Good. Okay. Well, the Burner Wallet was introduced by Austin Griffith. Griffin, right? Griffith. Oh, goodness. So he was using the XDAI chain, which was started by Igor. So Igor started a chain where you can move DAI, which is a stable coin on Ethereum, to the XDAI chain, and basically have that as a native token on the XDAI chain. And then Austin came along and said, well, that's cool. I have a stable token on a blockchain. I build a web wallet to use that as a kind of simple way to pay with a stable token, and just use a web wallet, opening a web page, creating a key on the web page or in the local storage of the web page, and use that as a wallet. And I remember several occasions where Igor was demonstrating Burner Wallet to me and gave me some XDAI, and I distributed it around as well, and I was also very intrigued by the simplicity of that kind of wallet, because it's really kind of taking off the edge of crypto. It makes it super easy for everybody to get the first coins, but it's also super easy to lose the first coins. So basically, having that one, we said, well, that's cool. We want to build the Minerva app for the ARTIS blockchain, but having something until that one is finished, we also fork the Burner Wallet and create a Minerva Burner Wallet, which is connected to the ARTIS blockchain, where we can move assets on the ARTIS blockchain. And this one I'm going to show you in a bit. I think one really important part, what was for me all the time, is like getting across that that a blockchain system is just kind of a basis. It's not something which has any kind of massive there needs to build applications on top of blockchains, in my opinion, to make it more than just a coin. So if you're in the coin space, of course there is a Bitcoin, and that's basically it, what you can do with a Bitcoin. But since the introduction of Ethereum, you can think of more to do with a blockchain system. So I like that kind of quote, although it's from a bankster. Blockchain is not the thing, it's the thing that enables the thing. So basically, I think that you can build a lot of things on top of blockchain systems. I'm deliberately saying blockchain systems. So various kind of systems having various kind of applications on top of them, and on the next layer you're probably interacting with several of them. And I don't know if you know that kind of movie. It's like about value and what is valuable. You know, anybody doesn't know it. So it's like a Stone Age kind of movie. Kind of somebody's trying to pay with gold, while gold is not introduced at that time. So no? Well, it's a cool movie, so I show it to you. So if you don't know it, you can look it up. Oops, sorry.
Redskins, Dollarheads, tepid lemonade. Get out of it. Redskins, Dollarheads, tepid lemonade.
Hey mate, I'll take 5 of your Redskins and one of those tepid lemonades.
It's one chicken, mate. It's not a chicken.
No, that's much better than a chicken, my friend. That is gold.
What?
Gold. The currency of the future.
Great, come back in the future.
Redskin! But no, mate, I don't think you understand. This has unlimited use.
Can I eat it?
No.
Can I wear it?
No.
Can I use it as firewood?
No.
It's starting to sound pretty limited, mate.
But you can melt it and then turn it into whatever you want.
Can I turn it into food?
No, you can't eat it. Is this going to take long? Hold your horses, mate. We are dealing in futures here. Oh, what's that? Is that a rock?
No, worse. It's cold.
Oh, cold? How do I get some cold? Gold. I have people mining for it.
Oh, you have people? La-dee-da.
We got a rich one here, eh?
What do you pay them with?
Gold.
Next.
No, they say that this currency could be worth 1,000 Ratskins, maybe even more, in just a few years.
Says who?
The people with gold.
Fuck. Next.
Look, every economy ever has been controlled by the big chicken banks.
Next.
And this is our opportunity to get out from under the big chicken boots,
Fuck me.
shake up the market, and start taking back our economic independence. Are you with me?
No.
Really? Come on, man. Look, all my mates are doing it.
I'll just get your hand off it, all right?
trying to predict the next alt rock. First it was stone, then bronze, then iron, now gold. What can I even do with this shiny shit? Make fucking jewellery out of it or something? Yes! Yes, you can do that. Great idea, because it's malleable. And, best part of all, there's fuck all of it. It's a finite resource. Mate, I'll tell you what a finite resource is. My fucking patience right now. Piss off! You know what? Stuff it. I'm taking it back. It's like talking to my dad. Yeah. Why don't you go discover avocado and smash it on toast, you dickhead? Yeah, maybe I will. Sorry, mate. I'll have a dodo head, thanks. Half a chicken. Piss on me, not you two. Oh, no. This is way better than gold. It's silver, or as I like to call it, like gold cash. It's faster to mine. It's... It's got to be the last one, surely. Ratskins, dodo heads, very tepid lemonade. Get it here. Desert warm.
So I hope you liked it. I think in the crypto space we still have to feel a little like that. So it's we're those which are kind of trying to convince the others and saying, well, we're looking at something big here, and then basically we still have a lot of people which are saying, no, that's not going to fly, and so don't be kind of disillusioned by these kind of surroundings. Of course, if you're living in a bubble, then everybody's kind of euphoric on it. But if you're not, then it can be quite hard. And I think that actually, and therefore I put it here, having something closer to, let's say, to the application layer, like what we do here with Minerva or Minerva Burner Wallet, helps a lot to kind of erode this kind of difficulty, getting it to the people and making them understand that it's super easy to interact, and that you don't have to explain them how to handle a hardware wallet or how to handle MetaMask or something like that. So this is like, because it's immediately scaring off people which are far away from the space. So from the application stack, what we do is actually we have Ethereum as the core blockchain, where I think that we're seeing a kind of decentralized finance system evolving. So on top of that, blockchains like ARTIS, POA, XDAI are considered side chains to Ethereum, which have bridges to connect to Ethereum, and where you can move assets between those chains. And Minerva, even, I mean here rather the application or the mobile app, but Minerva Cash or Minerva Burner Wallet is rather closer to the user, easy interaction, make it simple to explain, but as I said, so also easy to lose the coins if you're not cautious. So what I wanted to do here is, I think there are still a couple of people which don't have ATS, so the ARTIS coin. So if you want, I distribute 42 coins to everyone. So from my private stack, so I don't have to give this into my bookkeeping. So if you want to take part in the lottery at the end, you need to open minerva.cash, whatever kind of preferred browser you're using. So we play a little lottery game at the very end. So no interest. You don't have a mobile connection right now here. No connection. Yeah. You can go into the Wi-Fi. So who is already there? Good. Come to me. And hit receive. Come here. So. So who's next?
Da kannst du das hinschicken dann, ja.
People know.
Just nicht genau burn it.
So we have maybe some more information. So we have taken a lot of features out from the original burner wallet. So if you open the xdai.io, you create a similar wallet which has much more features. But we wanted to have it as basic as possible. So it's just ATS, it just has receive and send, and a couple of extra features, and not all the nice things you have in the original burner wallet, where you can move funds, where you can exchange them with others, and so on. So there is a lot of more features included in the original one. Important, you should get some security considerations. So in advanced, you have basically up there the private key, and you can hit show private key, then you see a QR code which basically has your private key encoded, and we should actually have there in readable form as well. Then you can copy private key, then it copies it to the clipboard, and you can move it some safe place. And you can hit burn private key, where you get another warning before you actually confirm that you're burning now the private key. If you have not backed it up, you have no chance to get back to your funds. So this is just important, but also don't use that kind of key if you think that it might be compromised. Basically burn that private key, move the funds to some safe place, and that safe place could be some private key you generated somewhere else with a derived kind of public key for it. So you can also import a private key in that field, or import or create one with a seed phrase. You can create basically your own one. Or
does burn private key means he generates a new one?
Yes. So once you say, well, that's not a safe one anymore, burn it. Move your funds first. Good. So and down here you can send a text, and you can create a possibility to do encrypted messaging between two, because basically what you're having in your hands is a private public key infrastructure. You can do encrypted messages between persons, and you can build up that kind of connection with sending something with your transaction, and then you can retrieve from that information the public key, not just the address.
Silent but not encrypted, so it's on-chain.
Yeah, the first one, right? And then you can start encrypted communication, because you then know the public address of the recipient.
No, everything.
Of the sender.
Yeah, everything is, as far as I remember from my last usage, it was in Denver in February. It was unencrypted on-chain.
Yeah, the first one, but the other one should be then encrypted, because he can retrieve the public key, and you can encrypt with the public key of the sender, and then basically you're starting. No,
not yet. But it's a good feature to implement.
Yeah, I thought it is in that way implemented. Never used it.
Simple transaction message.
Well, the first one is included into the transaction, and then because of the additional kind of parameters you send with a transaction in Ethereum, you can derive from the address the public key. And then with that public key, you can basically encrypt a message, and then the other one has the private key to decrypt it. So that's the basic idea, how you can, and as Austin actually said in one of the presentations, he said it's not recommended to do it that way, because basically you're having a public transaction on the blockchain. Everybody can see that kind of, can create the public address for that address the public key for that address what you used. So everybody can do
So
that.
you know who is talking, but you don't know what he's talking?
Yeah, right.
You also don't have don't have forward secrecy as well. So you always encrypt with the same key.
Yes, you always
More
encrypt it.
messages
So
is
it's less secure in a way.
So now it's proof of concept.
Yeah. No, it's just not that kind of super secure as others, of course. So let's do a little lottery game. So you open your wallet, or you still have it open, and we created a very, very super basic kind of lottery game where you can send exactly 5 ATS. Everything else will be rejected by the network. And it will be collected for 5 minutes, and then the next transaction, which is sent outside of those 5 minutes or 60 blocks, will get the winning pot. So basically, the more is in, at some point somebody sends it after the 60 blocks, and then everything will get to that particular address. Okay? Yeah.
But what is the incentive to send early?
None. It's just like everybody is paying in. The more you pay in, the more likely it is that you get the whole pot. Yeah? So that's the, there is no incentive to pay early, or there's no incentive to pay late.
Oh, I got the winner thing wrong. So the winner is chosen random. It's
Yes.
just a transaction after
But
the
it's
time is just starting selecting the winner, but he isn't the winner. Okay.
Yeah. So, and it's very simple. So it's like it would be possible, of course, that if you have a real lottery game with a lot of transactions, that the nodes could kind of influence the outcome, which is definitely not happening here. But in a kind of if you want to create a lottery game more sophisticated, this is not the code you should copy. So this is like a little bit too kind of basic, let's say. So to give you a little better impression, so let's go here. So basically that's the Block Scout blockchain explorer, which is also created by POA network. So as you can see, we're using a lot of tools they worked on. So it's, in my opinion, the best open source blockchain explorer, and we kind of changed a couple of things there to some kind of internal things on the blockchain explorer. So you find it as under explorer.sigma1.artis.network. You can also go there from artis.eco, and that's one of the kind of lottery contracts here. And if you want to see the code, so basically here you have the source code of the smart contract, the lottery smart contract. So basically it is kind of starting counting as soon as the first payment comes in, and after 60 blocks it will just be triggered that it pays out the full amount to a randomly chosen address within the set of payments within that contract. And that's basically it. It's not more than those couple of lines. It's more text than actually code, actually, if you look at it. So it's super basic, not very sophisticated, but probably is a nice way to look at various kind of codes within the system. So if you're deploying something, and if you're upload the code, so basically it's comparing that the binary you deployed to the blockchain is the bit code which is deployed to the blockchain is the same as the one you are kind of showing. So there is a kind of verification in there as well. So yeah, so the point, there is a nice feature here in BlockScouts. You can show the QR code, and because we have a lottery game, so I will just make it big enough so that everybody can shoot that QR code from staying at his place, and I will not take part. So you can play around and try to get pot. Igor, when do you have to go?
For the last day.
Now?
Yeah, like in 5 minutes.
Okay. So, does it work? So remember, you have to send 5 ATS. You should not send more or less. Otherwise, well, you can do. You will see the results in the transaction log.
Thank you for contribution.
So, huh? Volksnummer? Okay. Should work.
You can send multiple tickets.
Okay. What's about the message? So.
Oh, you use send, and basically when you go to send and scan that QR code, it should be possible to send to that particular contract address.
Yeah, but you mean the custom message, right? So you can also put a custom message in and say something like
Yeah, sure. If you want to do that, you can do that as well. Smart contract doesn't care. So, does it work or not?
Yeah.
Yeah.
You should see it in blocks.
Yeah, right.
So something that still needs to be changed if you click on the...
Oh, I'm sorry. So,
the colorful
80 ATS.
So, we have 80 ATS here. So here are the last couple of transactions. Somebody, yeah. So 90 ATS. Still counting. Come on, guys.
The repeat button is
Yeah, no, this one is missing. It's not that easy. So do it again, do it again, do it again. I already thought that one is that really is missing. So it's like, okay, just pay again, pay again, pay again. So it's like those automates where you just like, I play it again, I play it again, I play it again.
Let me spend all my money on this now.
You know, it's like I was using one of those contracts when I gave a lecture at university, and I just gave them 10 ATS each, and then nobody could pay twice because 5 and 5 plus transaction fees is more than 10. So I was kind of not thinking about that. So yeah. Yeah, with 42 you could.
42 is also the answer to everything, right?
Yeah, sure.
It's exactly the point there.
Yeah, I think 40.
I'm already in there with
So where? Oh, somebody.
Reverted.
Yeah, somebody tried to send 0. It was kind of funny because at university I did not specifically say, I said, well, you can send 5 ATS, and then we had like 8 ATS and 4 ATS and so on. So, yeah.
It was all red.
It was a lot of reds there. So the pot is still full. So after 5 minutes of transacting, 3 minutes ago, so 2 minutes to go. If all validators are up and running, we will have those 60 blocks in 5 minutes. So everybody who is not sending anymore doesn't trust the contract, right? I can say Didi rolled it, so it worked 3 times, so it should work this time as well. Yeah. So don't spend all your money, so otherwise.
And the winner is paying a round of beer for everyone.
Sure. Yeah, 1 minute to go. Then we should.
What's the last thing? That was me, because I did wave.
Huh?
There's a winking wave button.
Really?
Yeah.
When you say wave, it's a transaction. It's a transaction. When you press wave, it's a transaction.
And without content.
Yeah, that was the area.
When you press wave, you create a transaction on chain.
An empty transaction.
An empty transaction.
It's got to be like.
Yeah.
That's the wave.
Oh. That's waving to the blockchain.
Yeah, waving to smart contracts.
Did you pay a fee?
But this kind of waving helps if you want to send this message, and then you can kind of create that kind of public key, and then you can encrypt, can start this encrypted kind of conversation. So, oops, somebody already got it. Who got it?
Wasn't me.
So, okay. So you have a couple more now. Yeah, that's a nice thing. In that kind of settings, everybody is honest and say, well, it's me. So please prove to everybody else who doesn't trust that you have received it. So the smart contract is empty, you can see. So it's 0 ATS now. So everything...
Don't receive which address got the payout from this one?
The outgoing transaction, you don't know who owned it.
Oh, okay. Yeah, of course, but you gotta see that.
Where can I see it?
I don't know. I thought there might be a chance.
Maybe read open.
There must be outgoing transaction.
Somewhere.
No, we have it here. Yeah, sure. So we have the winner. So Joseph is paying everybody a beer. So just to conclude on Minerva. So you saw. Okay, thank you for coming. Bye bye. To conclude, so basically. Take care about the private key, or import the private key you created somewhere else into the wallet. Make sure that it's not kind of floating around somewhere on a cloud or something, or in an unencrypted email. And what we're working on is basically to connect Minerva, the Minerva wallet, Minerva Burner Wallet, to something which is an app. So basically you can move the funds to the app, which has a much more secure way of storing. The other thing what I'm currently testing and using is basically NFC card. And this card is able to create on that card 256 key pairs, and if I like here, I printed out the first couple of keys, so I can scan with the Minerva Burner Wallet. I can scan one of those keys and send it directly onto the address of that card. And then I have another application where I can read out the NFC or the address from the card, and I can transfer it with an on-card signing transaction. So the private key on that card never leaves the card. So that's the major part. So basically, that card does the signature of transactions, but the private key never leaves the card, and you cannot access the private key. So that's something which is fairly useful for people which are unable to handle private keys. So, and I'm pretty sure that's the majority of population. So we're using that in that setting so that you can actually move the funds there and then kind of get it off with the NFC enabled device.
But it means if you lose the card, you lose the money. I mean,
right.
Anybody can get the money from the card. I mean,
right. You can even destroy it. You can
that as well.
You can give it to somebody. This is like transferring money. And of course, if you're losing it or if it's going to be stolen, the only thing what you can do that the thief can not access it because you can PIN protect it. So you can do a PIN protection, but nevertheless you can't access it anymore yourself.
But how can you program the PIN there?
There is, it's pre-prepared that you can program a PIN on that card.
But how sophisticated is it? If this 4 digits or what is it? How long can it be?
I don't know actually if it's 4 or 6.
Is there some timer for tries or something?
I don't know that one either. I can't remember the specification.
I mean, in the case of scratching the card or the chip, the NFC chip?
Well, if you destroy the NFC chip, that's like destroying money or destroying keys, basically.
Because you cannot make a backup.
Yeah, you cannot make a backup. So that's a good thing and a bad thing. So it's like...
It's just different.
Yeah, it's different. So it's like it has the advantage of not being able to do a backup, because also backups have their security vulnerabilities. So it's sometimes maybe easier to keep that card, and you know, after 1 or 2 years you're moving it to a new card and say, well, it might at some point not function anymore, and then but of course you have to hide it quite well. So if you put there some more.
There's only one copy.
Yeah.
So nobody can copy it without you knowing.
The advantage of not able to access the private key is you can trust someone who gives it to you that he doesn't keep a copy for himself.
Isn't it possible to import the private key?
There is one address where you can import it. Yeah. On key 0, on the first one, you can import the mnemonic to create it outside.
If it's a normal Java card, I can write my own applet and then...
It's not a normal Java card.
But it should work with a normal Java card.
It is not Java card.
Yeah, but if I get a card from somebody, he could give me a Java card, and then I cannot be sure that there's only one private key.
Yeah, in that case, the private key is created on that card. It's not a Java card.
Yeah, but I cannot verify that.
Yeah, the point is, how do you verify that this is an original card which cannot be copied?
Okay.
I think that's what you want to say.
Okay. Yeah.
Probably a manufacturer certificate or something would also be on there.
I don't know what could give you the kind of ability to check it if it's original or if it's just a Java card with something written on it which looks like this card.
It's a valid point because it breaks some use cases. If you can have a fake card where you're able to read out the private key.
You don't know if the ledger is produced by Ledger, so it might be some Chinese mock-up which is
happy you insert some field
yeah.
private key.
So sure, Definitely, yeah. It could be a similar made Java card, and if you can't verify it, then that's an issue.
That's a pretty good use case. We should sell some cheap ledger devices.
I'm pretty sure you get them in China. So, yeah, that was about Minerva Burner Wallets and basically some surrounding ideas, what we are testing and currently trying to make them as a kind of usable ecosystem where people actually, even lay people can use blockchain tokens without having kind of, yeah, dealing with private keys and all the security elements, what most people have no awareness of. Cool. Any question? No. So Joseph is buying beer. Let's go for it. Thank you.